Okay, so in this video, we will look at the so-called alternating series test, which is a very simple test that tells us when an alternating series converges. So here are the assumptions. We assume that we have a positive sequence in Bn, and if Bn is eventually decreasing, and in the limit as n goes to infinity, Bn approaches 0, then the corresponding alternating series, B0 minus B1 plus B2 minus B3, and so forth, converges. Now, of course, the starting point could be anything other than 0, and the first term could be negative, it doesn't matter. The whole point is if you have an alternating series, you have to look at the positive part of the sequence, that is Bn, so the sequence without the alternation, and if this sequence is at some point on decreasing and shrinks to 0 in the limit as n goes to infinity, then the alternating series converges. Let's look at a very simple example of this, and then we'll consider in our next video a proof of this result. So let's look back at the example we considered in our previous video. So we looked at the alternating series, summing from 1 to infinity, negative 1 to the n plus 1 over n, summing from n going from 1 to infinity. So we can write out the first few terms of our series to get a feeling for what kind of terms we're summing, and if you do so, you will obtain 1 minus a half plus a third minus a quarter plus a fifth minus 1 over 6, and so on. So the negative 1 to the n plus 1 gives us the alternation in sign, so this clearly is an alternating series, and the test says you only have to consider the positive part of your sequence. Well, here, if you ignore the negative 1 to the n plus 1, you're left with 1 over n. So Bn is quite simply 1 over n. So, is Bn eventually decreasing? Well, the answer is obvious, right? Because Bn is 1 over an increasing function. And 1 over an increasing function is always a decreasing function. So clearly, Bn, which is 1 over n, is decreasing. Again, as it is 1 over an increasing function. Now in some cases, it may not be so obvious that Bn is decreasing, so of course, you can always fall back on the following argument. You can look at the continuous analog of the discrete sequence. In this case, we would look at 1 over x. And to show that something is decreasing, well, you have to show that the derivative is at some point negative. And again, we only care that the sequence is eventually decreasing. Therefore, if x is large enough, then we hope that the derivative will be negative. And if that's the case, then the sequence is eventually decreasing as the continuous analog would be decreasing. So in this case, you would say, well, avoid the quotient rule by rewriting 1 over x as x to the negative 1. Differentiate now from the power rule, you'll get negative x to the negative 2, which you can write, of course, as negative 1 over x squared. This is always positive. Negative 1 over something positive is clearly negative. So the derivative of 1 over x is always negative. Therefore, 1 over x is decreasing. Therefore, 1 over n is decreasing as well. So you can always fall back on the derivative when Bn is not clearly eventually decreasing. And keep in mind, if you use this argument, the derivative may be positive for some small values of x. But the key word here is eventually. Therefore, you have to show that when x is large enough, the derivative will be negative. So first part, check. Bn is eventually decreasing. Second part, does Bn tend to 0 as n goes to infinity? Well, the limit here is trivial. As n tends to infinity, 1 over n clearly shrinks to 0. So the two conditions are met. The positive part of our sequence, Bn, is decreasing, check, and thus converge to 0 in the limit, check. Therefore, this series converges by the alternating series test. And of course, you don't need to write by the alternating series test. You can simply write AST, alternating series test. And as we've said in our previous video, a very interesting fact about this now convergent series is that it converges to ln of 2. And that's it.